In this very short video, I'll talk about violations of assumption in the maximum likelihood estimator. And there are two main assumptions that can be violated. One is independence of cases. And that simply means that if I have my data set, let's say in JASP or something, right? So my cases are my rows and my variables are my columns. Then these rows should be independent of each other. That means that I should not be able to predict like the second row from the first row more than I could do with my model alone. That's very typically the case in cross-sectional data, but usually not in like time series data, for example, where this is like 9 o'clock or 11 o'clock. Then I can predict that I'm like tired at 11 if I was tired at 9 o'clock, for example. Another time when this is not the case is when you have nesting data. So let's say when this is, for example, siblings. So sibling 1, sibling 2, and this is like a new family, family 2, etc. So let's say these are the brothers and sisters, and these are brothers and sisters, and like the next two rows are brothers and sisters. Then you can predict that the second case is more similar to the first case than you can predict with the dataset alone, or with the model alone. Now, why is this a problem? That's because in the FML function, if you go to that video, you'll see at some point that stuff happens and there's a sum in the log likelihood, and that sum is due to independence of cases, right? So we have the probability of let's say data set of person 1 and the data set of person 2 and the data set of person 3 equals the probability of the data set of person 1 given data set of person 2 and 3 times probability of data 2 given data 3 times probability of data 3 likelihood. But then if we assume independence, this just cuts out, then we're left with the product of these things, and then the log of that becomes a sum. So that's how we get to this independence assumption. Now this is violated. Some things can happen. For example, your standard errors will not be correct, or you'll simply be missing a lot that's happening at a different level as well. You might get type 1 error rates, so you might run into problems because you're simply estimating a likelihood that's not correct. Now there are two solutions to that. One is to use a correction for the dependence of structure, and there are some R packages for that. This you see quite often in survey data, for example, where you have like very complicated sampling design. And another is to use multi-level structural phase modeling. And in multi-level structural phase modeling, we can explicitly take the clustering into account, which is very nice. It also creates a lot of problems because it's very complicated to do sometimes. But typically at least random intercept models work pretty well in many softwares, and they're pretty easy to use. In a random intercept model, you're assuming that the intercept differ per group, for example. And then you can take some violations of this independence into account. In SEM2, every group or people can teach other students about topics. And for this year, we're going to do that with videos as well. So you can make a video and upload it to Canvas so that other students can see it. Maybe we can even put a few on YouTube as well. And then one of you can pick multi-level SEM up as a topic and talk a bit more about that. So I'm not going to talk about it here, but you can go into detail on that if you want and then teach your fellow students about it. The second assumption that can be violated is multivariate normality. So that's that every item is this bell shape, and like the marginal distributions are all linear, so you have these oval shapes. And that's an assumption. It's a very important assumption because this whole likelihood here just hangs on that assumption. That's where it comes from. It's also not an easy assumption to get around. It's not like we choose that just because we like the normal distribution. It's pretty much one of the only easy to use multivariate distributions with many items where you can model things. And there's some other things you can do, but Multivariate normal is really, for continuous data, like by far the best choice because there's so many good properties. So what's the problem if you have violations of multivariate normality? Well, the problem is also that we don't really know why multivariate normality is violated. So that can be due to many reasons, right? If your data is multivariate normal, that's okay, it's multivariate normal, but if it's not, it could be ordinal, it could be skewed, it could be like bimodal, things like that. Which is a bit of a problem as well, because it means that there's not an easy solution to it. Some consequences that can arise are that your standard errors are incorrect, and the chi-square test value is not accurate. So there are some ways to get around that. So what we can do is, instead of using the fit function, the maximum likelihood estimator, we have robust estimators. These don't really change the chi-square test, but they change the standard errors. So then your p-values are a bit more accurate, which is a good thing. And they're very easy to use. You just say estimator equals MLM for complete data or MLR for incomplete data in Lavaan. And especially the M plus package has like a lot of nice robust estimators as well, and also for ordinal data as well. Another thing you can do is you can use bootstrapping. Now bootstrapping is this method where we, let's say, take the data set and then let's say we have a row here, then we're going to generate new data sets from this data. Let's say I'm going to generate like 4 data sets here. And I do that by taking these rows and resampling them with replacements. So maybe this one here is entered like twice here, for example, and then we have this one here and this one here, something like that. And then maybe this case lands in here and this one lands in there as well one time. And again there, for example, and this one does land in there here. So you get like resampling of the same data over and over and over again. Now those we can then use to compute our SEM model. And that gives us parameter estimates. And then we can just see what these parameter estimates look like. The nice thing here is that we get an insight in the variability percent, the parameter estimates, by only using the real data. So we see what kind of uncertainty does this real data set look like if we go to use this estimator, which is a very nice and powerful method to use as well. Okay, that's it for the video on violations of assumptions.